David Clemens. I'm the Director of Engineered Product Sales for Wheeler. We have been members of the Short Span Steel Bridge Alliance since it was initiated in 2007. So I appreciate the opportunity to be part of your webinar series here. We chose to feature a project that was put together by the Forest Service in northern Wisconsin. So this is in the Chequamegon National Forest near Mellon, Wisconsin. We work with the Region 9 engineers on a variety of projects, and I consulted with Patrick Hampstead, who is one of the Region 9 bridge engineers. He may be on the webinar today, so he can critique the facts and figures that I shared today. But the project that we want to feature is a Forest Service bridge that ultimately utilized steel beams with a timber panelized deck to replace a superstructure that was being load posted. So we'll explore the advantages of using the steel superstructure and how it benefited this location. So the existing bridge, we'll go, well, to overview what we're going to talk about today, we'll review the condition of the existing bridge and the reasons for the superstructure replacement, what factors went into the selection of the replacement structure, including the local contractor pool, specifics for the plan development, the construction project process, and then options for combining steel beams with timber panelized decks in other applications. So this project was the Brunsweiler River Bridge on Forest Road 187 and structure 1.8. So the existing bridge was built in 1951 with steel beams and a cast-in-place concrete deck. The steel beams were in good condition and the concrete deck was average with areas of deterioration. But the bigger concern was that in 2021, the bridge was scheduled for an updated load rating to meet the current load rating criteria. And the analysis led to the determination that despite the physical condition of the bridge, it would require posting. And this was primarily due to the original design criteria. In 1951, the design vehicle was only H15 and the available steel was 33 KSI. The Forest Service engineers were not confident if the deck to beam connection was composite or non-composite, so they assumed non-composite, which didn't help in the rating. These combined factors led to the posting of the bridge and restricting ultimately the truck access. Considering this is a forest road and logging traffic is typical, the posting was going to be a burden. And so they looked for opportunities to upgrade the bridge, which ultimately led to replacing the superstructure so they could avoid the load posting. The foundations were in good condition and could remain in place if a new superstructure didn't exceed the weight of the existing bridge. Also, available contractor pools consist of smaller companies with limited resources. Keeping the construction simple and geared toward the modest equipment available to those contractors was a priority. The site is fairly remote, so limiting any ready mix deliveries would also control costs. Cast-in-place concrete or heavy precast components typically push the projects to larger out-of-town contractors who charge a premium to come and work in the forest. So this led the Forest Service to review options utilizing steel and timber. They have experience with steel and timber bridge components on many of their projects. They're familiar with the details and the cost and construction best practices. Steel is performed well at the site, and combining with timber components would provide a lightweight superstructure. Weathering steel was chosen for the steel finish. It has shown acceptable performance in this region with minimal maintenance. There would be concern with painted steel that future maintenance would be difficult with its proximity over the water. Also, weathering steel provides the preferred aesthetic in the wooded location. Panelized timber decks are lightweight. Being shop assembled, they speed installation and they provide added durability over a timber plank deck. There are many available crash tested railing details that attach to the timber decks, and that was a preferred option. And again, they provide the best aesthetic for the environment. Plans were developed by the Forest Service Region 9 engineers with a local IDI consultant. IDI means they're on basically a retainer basis. Coleman Engineering out of northern Wisconsin was the IDI consultant for this project. The consultant prepared the project documents with finished dimensions and conceptual details and standards for the design and materials, but it was to be a design supply delivery such that the bridge manufacturer was responsible to prepare the final designs and supporting calculations. So you see here, these were the details that were in the project documents showing the general geometry and the predominant features that they expected for the bridge superstructure. After the award of the contract, then final plans were to be prepared by the bridge manufacturer and submitted through the contractor for approval. So Wheeler was selected as the superstructure supplier. So we prepared plans for the bridge superstructure. The plans included expanded details for all of the bridge superstructure components. This sheet includes specifics for the deck panel layout. So again, it was for the manufacturer to determine those details. The steel beams were detailed using typical standards for bearings, stiffeners, and diaphragms. The deck panels are connected to the beams via HCP clips. We'll see that in more detail when we get to some of the pictures. The design is considered non-composite for the connection. So it does not, we do not take advantage of the deck in the beam design. But that's one of the things we have to balance when we're using timber panels on steel beams. Using the HCP clips only requires drilling the timber deck panels and not the steel, and this speeds in the installation and keeps the installation simple for the contractor. The Forest Service does have published details for crash tested railings, including TL1, TL2, and TL4, meeting the requirements of NCHRP 350. The railings connect directly to the deck panels and not to the steel beams. There is currently testing in progress to update these details in accordance with MASH standards. The TL1 has been reviewed. I believe there has been a report published. The TL4 is in progress. We've been talking with the people in Nebraska at the Midwest Regional Road Safety Facility, I think there's an acronym for it. But they expect to have the TL4 details available by the end of 2024. And then they will work on TL2 details based on funding and available time for additional testing. The final design calculation packet was developed and submitted to the owner and their consultant for review and approval. And then we were on to construction. Ritola was the selected contractor. They are local to northern Wisconsin. They performed the work. After removing the rails, they went and they cut the deck into sections. So I mentioned that we like to work with contractors that have less sophisticated equipment. And then I saw this big fancy saw and I'm like, well, that takes some sophistication to put a saw like that to work. So what they did is they went out and they cut the deck into sections and then removed them from the steel beams. This confirmed that the original design was not composite. You see there's no active connection between the beams and the deck. So the speculation that we had a non-composite design was confirmed when they did the demolition, but it did facilitate easier demolition of the deck and beams. You'll notice that they're doing everything with an excavator. There was no crane required for their activities. After the demolition was complete, the abutments were cleaned and modified for new bearings. And the beams were set again with 2 excavators, another example of working within the capabilities of the contractor. Bolted diaphragms were installed in 4 locations along the beams, again, using typical DOT standard details for stiffeners and diaphragms. Anchor bolts were installed using drill and epoxy method into the existing beam seat or bridge seat. Ultimately, the beam ends were cast integral with the abutment. So you see they have some formwork there for casting around the bridge beam bearings. I will admit these next 3 pictures are not from this project. I didn't have any action shots of the contractor setting the deck panels, but I thought it'd be important for you to see what are these timber deck panels, how do they arrive, and how are they installed. So here's an example from a project in Iowa where the contractor is handling the shop fabricated deck panels with slings and preparing to put them in place. Here's a typical panel being set onto the steel beams. The panels are typically detailed the full width of the bridge and cover about 4 lineal feet of the bridge deck. So you're setting the deck 4 feet at a time. Again, the panels are lightweight. They can be handled with an excavator. The panels are installed essentially with general labor. We don't necessarily need skilled iron workers or other trade classes to install the deck panels, and they incorporate typical tools that the contractor's going to have on hand. This shows how the panels are clipped to the beams. This is that HCP clip. We prefer this connection because we don't have to drill the steel. Also, the shape of the HCP clip, when it's engaged, it acts like a spring. So if there's any shrinkage over time of the timber, you have some reserve connection capacity because you've essentially tensioned that spring when you install the clip. You could bolt through the flange. That would require either shop or field drilling of the steel, which makes the connection a little bit more complicated for the contractor to line up. Sometimes we get asked, can you glue the panels to the steel? That's not a recognized connection, so no gluing of the panels to the steel. The railing components, so the curbs, scupper blocks, rail post, railing, they're all shop fabricated. So our goal is to do as much framing to the wood before we pressure treat. And then they arrive to the site ready to install with minimal field drilling. There are some components that do require field drilling, and then a field preservative is applied. They do attach directly to the deck, and with these details, they have to be attached after the deck is installed. You can see the various hardware for the deck panels. In this case, that hardware is recessed. Forest Service chose to use a timber wear surface as the overall protection for the panels. So at this point, they've got the majority of the rail assembled, and they're starting to install the wear plank. I'd like to point out that this bridge was built in essentially winter conditions. So that is one of the advantages of limiting the concrete that you're using on site. Steel and timber components are not temperature sensitive in terms of their installation. And so often that's an advantage to be able to schedule the work through the winter. And that would not be possible if we were considering a cast in place concrete deck. Once the superstructure was complete, the bridge could be immediately open to traffic. Again, this is important in remote locations where you may have long detours. So we're going to review the project timeline, and you're going to see that this went together very quickly. So looking at the timestamps on the pictures that were provided, the deck demolition was started at the end of October. They were installing beams roughly 10 days later. The wear course and railing were installed by the middle of November, and they were able to open that to traffic November 23rd. So essentially 30 calendar days from demolition to being open to traffic. So a very quick installation relative to other options. Once the weather permitted, the contractor came back and added the approach railing and basically buttoned up and completed the project. So this is the bridge this summer and has been finished and being used. A closer look at some of the details. Here is a close-up of the railing detail. Again, this is considered a TL4 NCHRP approved railing detail. And you have curb and scupper block elements attached directly to the transverse panels, then the rail post attached into the curb and the railing attached to the rail post, and with offset blocks to align the rail with the face of the curb. So fairly typical detail, and again, published standards for this. It does require a minimum of a 6-inch timber deck. Most of our projects will see decks, and 6 is a nominal dimension. They're somewhere between 5.5, 5 3/4 in actual thickness. Depending on beam spacing and the vehicle load, we may use an 8-inch deck. But as we mentioned, 6 inches is the minimum for the crash test rail. Here's a shot showing the beam and the bearing attached to the recycled abutments. And you can see that everything fit within the confines of the original abutments. So a pretty clean detail. And here's the finished bridge, and you can see how the combination of weathering steel and timber components fit very well into that forest environment. And that was one of the goals for the Forest Service in selecting the materials for this project. Some of the specifics: it's a 61-foot span. It's a 14-foot clear roadway. So these Forest Service roads are essentially single lane. But that gives you some perspective of what you're looking at. So we have a similar project with the Superior National Forest in northern Minnesota. It is due to ship in September, and it's detailed very similarly. Here are the materials at our manufacturing facility ready to go. So we've got the weathering steel beams and the transverse timber deck panels, all shop fabricated, ready for the contractor. I believe they're working on the abutments right now. And in 2 to 3 weeks, these materials will ship and they'll start the superstructure installation. So reviewing some of the things to consider, the highlights of using steel beams with timber bridge decks superstructures. You have multiple finishes available, no different than other typical steel beam applications. Weathering steel, painted steel, hot dip galvanized. In the upper Midwest, we really don't see any metallizing, but in other parts of the US, you may see fabricators offering a metallized galvanized finish. Again, it's a non-composite deck to beam design, so that has to be considered when you're detailing the bridge. Simple installation, less sophisticated contractors, smaller equipment, not weather dependent. Crash tested railings available for TL1, 2, and 4, and multiple wear surface. This particular example used a timber wear surface. In some applications, we're using a simple chip seal. And then in other applications, we're using a full asphalt overlay. And I won't get into all the details, but there are specifics into how you detail the timber deck panels to best handle the asphalt wear surface. So that wraps up that specific project. I've got a couple minutes, so I think I'm just going to highlight a couple other installations that we've done that show some variations to the concept of steel beams with timber deck panels. This particular site, there was a flash flood that washed out the existing bridge, and there was a long detour associated with the bridge being out. So the county and the town were looking for ways to expedite getting a new bridge put back in place. And in doing that, they used a design supply contract to get the design and materials on order. And while the bridge plans were being developed, they let installation contract. Ultimately, it took about 2 months of planning, 4 months for the material fabrication, and about a month to build. So they were able to get a bridge back in place in about 7 months. The traditional design bid build that a county DOT process would implement would take an estimated 18 months. And so in half the time, we're able to get a bridge back in service. Another example, in this case, they used painted steel. Originally, they were going to use weathering, and then the county decided to transition it to painting the beams. So they ended up with the final detailing looking like this. Again, we used the HCP clips to attach the timber deck to the steel beams. This avoided any field drilling of the steel and any touch-up paint required to that field drilling. Another example of replacing a superstructure but recycling the abutments. So again, the combination of steel and a timber deck provided a lightweight option and reduced the total work required at the site. Basically, they removed the superstructure, cleaned up the bridge bearings, and then installed steel beams with a timber deck. Again, in this case, they chose to use painted steel for the beams, and they utilized a TL2 railing detail, a little bit lighter, but again, attached to the deck panels.